Hello everyone, and welcome to a proof of the relationships between the force, the mass, the speed, and the radius of an object moving in uniform circular motion. Consider an object moving in a circle at a constant speed. Here's the circle it's moving in. At some point it will be here, we'll call that point A, and a little bit later it'll be here, point B. We can, of course, draw on a radius from the center of the circle to point A and then draw in the velocity vector. That velocity will, of course, act tangent to the circle, therefore at a right angle to the radius, and we'll call that V sub A. Likewise, the velocity vector at B can be drawn after we draw the radius. It'll be perpendicular to that radius, tangent to the circle at point B, and that will be the velocity B. So it starts at VA, ends at VB. Now, we know that this object is accelerating, as we discussed earlier, and therefore that Newton's second law should apply. And Newton's second law says net force equals mass times acceleration. And you'll notice that we already have two of our variables, force and mass. So really what we need to focus on now is how can we prove what the acceleration of this object is as it moves in uniform circular motion. Well, first of all, average acceleration, that little line over the top means average, is change in velocity over change in time. Change in velocity is, of course, final velocity minus the initial velocity, which in this case is v sub b minus v sub a. Now, we haven't done vector subtraction before. However, we have done vector addition. And thankfully, vector algebra works just like regular algebra, that you can rewrite subtraction as adding the negative. So VB minus VA becomes VB plus the opposite of VA. Now we know how to do vector addition. We know how to in fact draw vector addition. We simply draw the two vectors head to tail. So let's draw a vector diagram that represents the change in the velocity. There is VB. Notice that it looks exactly the same as VB here. Plus means I draw head to tail, so I'm going to start here. The opposite of VA. Now the opposite of VA would be a vector that is just as long but points in the opposite direction. So there we go. There's the opposite of VA. The resultant vector goes from the tail of the first to the head of the last. And the resultant vector is VB plus the opposite of VA, which is VB minus VA, which is the change in the velocity vector. Notice here, directionally, the change in the velocity vector, if we were to think of that right here, points right into the center. Right? It's a centripetal acceleration that we're finding here. Now we can create a second triangle by looking at our original diagram and drawing a chord from point A to point B, which we can call the chord AB. And we now have two triangles. Right? The one composed here with the two radii and the chord AB, and the one here from the velocity vector diagram. Now those two triangles are actually related to one another. Let's see how. Let's start out by comparing the vertex angles. Now you can kind of see this in my scale drawing, but these vertex angles are actually congruent to one another. They're the same size. Now why do they have to be the same size? Well, think about this in motion as you've seen in other PowerPoints. Okay? Because the velocity is always tangent to the radius, it's always perpendicular, think of this as rotating from A to B. In rotating from A to B, the angle that the radius rotates through has got to be the same as the angle VA rotates through to get to VB. Because they're always connected perpendicular. So this angle's got to be the same as that one. Now, these are both special kinds of triangles. What kind of triangles are they? Well, they are isosceles triangles. How do I know? Well, look over here. These two sides are the exact same length. The radius is constant in a circle. And these two sides are the same length because it's moving at a constant speed, so the magnitude of the velocities are the same. So both triangles are isosceles. Now, if the vertex angles are congruent and both are isosceles triangles, then what has to be true about the four base angles? Well, my supposition is that the four base angles are also congruent to one another. Why? Well, we have, first of all, you know that the base angles in an isosceles triangle are congruent. There's 180 degrees in any triangle. If you subtract off the vertex angle in both triangles, you have the same amount of degrees to evenly break up between the two base angles. right, since they have to be congruent to one another. So therefore, the two base angles are congruent. And now notice we have two triangles that are not identical. They are not congruent triangles. However, they do have all three corresponding angles congruent. Reaching back in your geometry brain, I know that when you have two triangles that have all three corresponding angles congruent, those triangles are similar. Now, what's special about similar triangles, besides the fact that the corresponding angles are congruent? The corresponding sides are proportional to one another. So we can set up a proportion here between these two triangles. I can say that the change in the speed is to the speed, and notice here I'm losing the arrows for the moment because, I'm also losing the subscripts because the speed is the same on both. So this side is to this side what the chord AB is to the radius. So check that out again, this proportionality I can set up between the lengths of the sides. That's why we have to get rid of the vector parts. We're just doing proportional lengths of sides. Well, let's take a look at this now. I don't really want to get the average acceleration out. I want the instantaneous acceleration. How are we going to get the instantaneous acceleration? Well, if you think about what we've done in the past, what we could do is to shrink the time interval. In other words, move the points closer together. Right? The closer we make the points, the closer the average is to the instantaneous value. And if we take a limit, little pre-calc idea here, the average will become the instantaneous value. But when we do that, one other thing is going to become important. Look at the chord AB. Compare it to the arc AB, the distance here along the arc from A to B. Now, right now, they're different lengths. But as we shrink the time interval, what's going to happen? That's right. If you look at a smaller and smaller piece of a circle, it begins to approximate a straight line. So as we shrink the time interval to 0, not only will the average acceleration become the instantaneous acceleration, the acceleration at point A, but the chord AB can be replaced with the arc AB. So let's make that substitution. There we go. That leaves us with a proportionality that says that the change in the speed is to the speed what the arc length AB is to the radius. Okay, next step. Remember that this object is moving at constant speed. Since it's moving at a constant speed, the speed is simply the distance over the time. But since it's moving in a circle, the distance around once is the speed times the time. And the distance in this case is the arc AB. Right? Do a little algebra here. Distance is speed times time. That's really our toy car lab equation. And then the distance is the distance from A to B, which is the arc length AB. Substitute that in. We now get a proportionality that says the change in the speed is to the speed what the speed times the time is to the radius. A couple steps of algebra. First of all, multiply both sides by the speed. That gives us speed squared times the time over the radius here, and over here the change in the speed. And then let's divide the time, both sides. And we get the change in the speed over the time is the speed squared over the radius. Now, I hope in some of your minds, at least, there's some bells going off here. What is the change in the velocity over the time? The rate of change of velocity. How quickly your velocity is changing? That's right, it is the acceleration. Therefore, we have just proved that the centripetal acceleration of an object moving in a circle at a constant speed is simply its speed squared divided by the radius. And since Newton's second law says net force equals ma, substitute that in, and the net force acting on an object moving in a circle at a constant speed must be equal to its mass times the speed squared divided by the radius. And that, of course, is exactly what we found in the lab. So take a look back at this. Watch this again if you want. It's kind of a beautiful proof to see all that we did here, all of the different physics, Newton's second law, some constant velocity. What else do we do in there? Definition of acceleration, vector algebra, right? Some pre-calculus ideas, some geometry, all of these things going together to make these equations. Right? So the physics predicts the relationships, and so did the lab. And so, hopefully, you believe that they are true.